We are Group 6, and our project is titled CFD Parametric Analysis of an NACA2412-based blood profile using unset fluent. This project focuses on using CFD simulation to study the aerodynamic behavior of an NACA2412 airfoil, which is used as a simplified blood profile. In the study, we analyze pressure distribution, velocity field, turbulent kinetic energy, lift, drag, and aerodynamic coefficients. We also compare our CFD results with published literature to check whether the flow behavior is reasonable. For the group work, Zhang Quan was responsible for CFD simulation and result extraction. Abdullah Najim Abdullah was responsible for geometry, mesh generation, and boundary condition setup. Xu Libin was responsible for literature review, discussion, report writing, and presentation preparation. This slide shows the overall summary of our project. The CFD model captures the expected NSA2412 flow physics. The main evidence comes from the pressure contours, velocity contours, TKE contours, force results, coefficient results, and literature comparison. For the base case, the lift is 2.6525, the drag is 0.075, and the lift-to-drag coefficient ratio is 28.28. The maximum skewness is 0.60021, so the mesh quality is acceptable for this coursework level CFD study. The main technical conclusion is that the pressure field shows high pressure near the leading edge and low pressure on the suction side. These pressure differences create lift. The velocity and TKE contours also show flow, acceleration, and wake mixing. Overall, the simulation results follow basic aerodynamic theory. This slide explains the literature basis of our work. The purpose of validation is to check whether our CFD results show similar flow behavior to published NACA2412 studies. We don't expect exact numerical matching because different studies may use different Reynolds numbers, mesh settings, domains, and turbulence models. The selected papers support different parts of this project. GONG support pressure and velocity control validation. Volkovo support the discussion of turbulence model sensitivity. Agumoscork and Anima support the angle of attack trend. Cicerum provide reference for wake and separation behavior. Marisha and Rajendran support the use of C-domain and near-wall mesh refinement. Therefore, our validation approach is based on comparing flow structures and aerodynamic trends, not exact coefficient values.
NACA 2412 is a compared profile suitable for a simplified blade suction study. The geometry is reproducible from coordinate and can generate left a small angle of attack. NACA 2412 code meaning 2% maximum chamber at 40% chord and 12% maximum thickness. This chamber created pressure difference between upper and lower surface supporting lift generation. Design choose a 2D airfoil profile. 2D airfoil profile is simple enough for controlled CFD studies while still showing important turbomachinery flow ideas such as pressure, grinders, boundary layer, behavior, and wake losses. The simulation workflow links geometry, mesh, solver, physical, and post-processing. Each stage product evidence used later in the validation and parametric discussion. 1. Geometry imported NACA 2412. 12. Coordinate and from the 2D airfoil profile. 2. Domain. Place the profile inside a C-shaped conventional domain. 3. Mesh. Final near the airfoil, leading edge, trailing edge, and wake. Solver. Used steady pressure based fluent setup with the SST K omega turbulence model. 5. Result. Extract contours, forces, coefficient lift, coefficient drag, coefficient lift / coefficient drag, and quality of flow behavior. The C-shaped domino reduces fire fault influence and levels room for wake development. Boundary conditions reflect the physical flow path around the airfoil. Boundary logs velocity inlet upstream, boundary number 2 pressure outlet downstream, number 3 non-slip wall on airfoil surface, number 4 downstream region capture wake, number 5 AOA and inlet velocity can be changed independently. Two simulation uses a steady pressure based setup with two control parameters. The design point log keep one variable fixed while change the other item. Solver treating pressure based approach steady state working fluid air turbulence model assess TK omega outputs pressure velocity TKE left drag parameter set on AOA fixed at 5 degree inlet velocity varied at 2.5 and 5 and 10. Parameter set up to velocity fixed at 5 angle of attack varied at 1 and 3 and 5 degree. Control variable processable only one parameter change in each study, so the trend can be interpreted physically. Mesh refinement is focused near the airfoil and wake, where gradients are strongest. The mesh quality is acceptable for coursework level CFD trends analysis. This photo overall mesh distribution, then airfoil wake refinement. Notes 51,189 and element 100,296 and max sequence 0.60021. Maximum swings remains below the 0.9. Target local refinement helps capture wall and wake effects.
Now I will explain the main safety result, and the base case is at the 5 degree angle of attack and 5 meter per second in net velocity. And this shows that the NACA 2412 profile can produce useful lift, and this lift is much larger than the drag because the cambered airfoil create pressure differences between the upper and lower surface. And this slide shows the static pressure contour. High pressure region appear near the leading edge. It is because the incoming flow slowed down when it first meets the airflow, and on the upper surface the pressure is lower because the flow move faster over the cruise surface, and this pressure difference is the main reason of the lift generation. The result is also similar to the pressure pattern reported in NSA 2412 literature. This slide is about the velocity field, and the flow accurates over the upper surface of the airflow. When the inlet velocity becomes higher, the higher speed region becomes stronger. And behind the trailing edge, a weak region can be seen. This means the airflow change the flow speed and create a weak after the airflow. This slide shows the turbulent kinetic energy, or TKE. TKE is the higher near the airflow surface and behind the trailing edge. This area is the weak region where the upper and lower flows meet together. When the inlet velocity increase, the TKE also increase. This means the higher speed can produce more lift, but it can also create stronger wake loss. So higher force is not always better. Yeah. And this slide shows the two parameter studies. For the first study, the angle of attack is fixed at 5 degrees, and inlet velocity is changed from 2.5 to 5 and 10 meter per second. For the second study, The inlet velocity is fixed at 5 meters per second, and the angle of the attack is changed from 1 to 3 or 1 to 3 and 5 degrees. This is important because only one parameter changes at one time, so the result tree is easier to understand. This slide shows the effect of inlet velocity. It happens because higher velocity get higher dynamic pressure, so the CL over CD value also increase from 2022 0.84 to 33.91. So the airflow performance improved in the testy range, but the wake and turbulence also become stronger. So overall, these results show that inlet velocity and the angle of attack both affect in NACA 2412 blend's profile, and higher velocity and higher angle of attack can increase lift, but they also increase drag, wake missings, and aerodynamics looks.
This slide presents the validation and literature comparison. Our CFD result agrees qualitatively with published NACA 2412 pressure behavior. In both our result and the literature result, high pressure appears near the leading edge. This is reasonable because the incoming flow slows down at the leading edge and creates a stagnation region. Also, lower pressure appears on the suction side of the airfoil. This happens because the flow accelerates over the upper surface. The pressure difference between the upper and lower surfaces is the main source of lift. The velocity field also supports the interpretation because it shows upper surface acceleration. In addition, the wake and turbulent kinetic energy trends are consistent with the reported wake and separation behavior in the literature. Exact numerical agreement is not expected because the Reynolds number, mesh, domain, and turbulence model may be different. So the key validation point is that our safety model captures the correct pressure pattern, velocity behavior, and wake trend. This slide discusses the engineering meaning, limitation, and future work. From an engineering point of view, increasing inlet velocity and increasing angle of attack can improve lift within the testing range. However, they can also increase drag, wake turbulence, adverse pressure gradient, and aerodynamic loss. So, higher lift does not always mean better blade performance. In blade design, we also need to consider efficiency, drag, wake loss, and flow stability. There are some limitations in this project. First, the model is two-dimensional, so it doesn't include blade tip effects or span wet flow. Second, the simulation is steady state, so it can't capture transient vortex shielding. Third, the tested angle of attack range is limited, so full stall behavior is not studied. For future work, with just adding grade independence testing, using a wider angle of attack range, conducting transient simulation, and developing a three-dimensional blade model if computing resources are available. The key defense point is that the model is suitable for a control safety trend study within the assessment scope. This is the final conclusion. Overall, the NACA 2412 safety study meets the project aim by explaining blade profile flow behavior through validated safety trend. There are four main takeaways. First, the pressure and velocity field shows the expected lift generating behavior. Second, the TKE controls identify wake mixing and qualitative aerodynamic loss. Third, the velocity and angle of attack trends are physically reasonable. Fourth, the literature comparison supports the flow pattern validation. In conclusion, CFD can support blade profile design decisions by connecting flow structures to aerodynamic performance trends. This project shows that unset fluent can be used to analyze pressure distribution, velocity behavior, wake development, and aerodynamic performance of a simplified blade profile. Thank you.